So good morning, students.
Good morning, sir.
We will start the today's lecture by continuing what we left yesterday. And if you give a little bit more attention in the today's lecture, all the asymptotic notation will get clear only by this thing. So you see on the top, I have given some functions: 1, log n, under root of n, and so these are all the functions which we will be using for describing the time complexity of any algorithm based upon the ascending order of their complexity. So the time complexity of an algorithm could be like constant 1, 2, 3, which is the first term. It could grow like log n, and log n means, suppose we are having n is equal to 32, and if this function grows linearly, it means this function is big O of n, which means again big O of 32. The total number of the places or storage spaces there are inside this array, if it is 32. Now, if it is like, if the complexity is not linear, it is logarithmic, which means log n and base is always 2 here. So when we put the value n is 32 here, because we are taking it as 32 total number of the storage spaces inside the array, and the 32 will be on base 2. So we can write it also like log 32 will be written as 5 to the base 2. And log 2 to the base 2 is equal to 1. So 1 into 5 will be equal to 5. So this complexity is very much lower than this complexity, that is 32. So this means that any algorithm whose complexity is logarithmic, that complexity is having less values than the linear one. And that is why in the presentation slide, I have arranged all these functions in the ascending order of their complexity. Log n, then under root of n, then n, then n into log n, because sometimes the complexity of algorithm can't be alone among as one of the functions from among those given functions. It could be combination of any one of those functions, like n square log n. Okay, it could be 2 power n log n, any combination of all those functions which are mentioned here. But these are the only functions which will be using as a representation for describing the complexity of any algorithm. Maybe they could be alone, or they could be combination of different functions. So accordingly, n square quadratic grows more than n log n cube grows more than quadratic, and similarly, when we reach to the right of this ascending order, we are having the exponential functions 2 power n, 3 power n, and accordingly n power n. Now, what we say in big O notation, which we described yesterday also, we said that the big O notation gets followed only if it satisfies this condition: fn should be less than or equal to a different function gn multiplied by a constant c. If this condition holds true, which means that this function could be written as big O of n. And big O of n notation of any algorithm gives the worst case, because this is the upper bound. It also means that at most this algorithm can take, if you see this graph here, this diagram, the time complexity of an algorithm is running time. This is called time complexity, and k into fn stands for c into fn. You can take k equal to c. So this is its big O. So this algorithm can take upper value up to this thing, but not more than that. Okay, so that is why it is at most. It can't go beyond that. It could be up to that or below that, but not more than that. Okay, so this gives the worst case scenario a function can grow up to this level or this mark. Its time complexity could grow. Okay, but not more than that. Now see here, an example is given, which is f of n is equal to 2n plus 3. A very simple example, and we have to find whether this condition, this equation, or this time complexity follows this criteria or not. So what we will do, just I will move very slowly, because if you understand this, you will understand everything in this asymptotic notation. So what I will do, first step, I will put the value. I will 2n plus 3. It is f of n. Isn't that arrow is there because this stands for f of n? Then I have to put this condition less than or equal to, that is here. Then forget about this 10, because this 10 is equal to c. Okay. Then here I have to put g of n. G of n is again n, which is linear in time, because the actual f of n is also linear in time. So we put g of n equal to n here. Now I have to see to which term I will multiply this n, whether I should multiply it by 1, 2, 3, 4, 5, 6. But the condition that 2n plus 3 should be less than or equal to, multiplying that n by that digit, it should be always this equality or less than sign should always be satisfied, है ना? तो मैं यहाँ से इसको मल्टीप्लाई कर सकता हूँ 1 के साथ भी, तब मेरा 1 जो c है वो 1 निकलेगा। मैं इसको 2 के साथ भी कर सकता हूँ, ये सब मुझ पे डिपेंड है। बट देखना क्या है मुझे कि जो ये राइट हैंड साइड है ये हमेशा बिगर होना चाहिए या इक्वल टू होना चाहिए लेफ्ट हैंड साइड। लेफ्ट हैंड साइड चूंकि जो हमारा f ऑफ n है, that should be always less than or equal to c into g of n. Now if I multiply it by 10, okay, you see that it holds true every time when n is greater than or equal to 1. n को हम 0 नहीं ले सकते हैं, because condition में ही दिया गया है is this condition that the two constants, that is c and n, they should be always greater than or equal to 0. ये हमने कल देख लिया, greater than 0. So we can take the example of c as 10, and we see whenever we put the value of n greater than or equal to 1. So if we put the value of n is equal to 1 initially, this function will become 2 into 1 plus 3, which means 5, and that is less than or equal to 10 into 1, that's 10. So when this function satisfied n is equal to 1, it means it will satisfy everything. Yes, when we put n is equal to 2, n is equal to 3, it will always satisfy, because on the right hand side we are multiplying it by c, which we taking equal to 10 at this very time. So the point essentially is to clarify that the right hand side should have less number of terms than LHS. On the left hand side of this inequality, we are having two terms, 2n plus 3. One is linear, other one is constant. There could be also some quadratic 6n square plus 2n plus 3. It could be like that. So big O का मतलब है कि हम इसको सॉल्व कर रहे हैं, जो इंपॉर्टेंट टर्म्स है उसी को हम ध्यान में रखते हैं और बाकी अनइम्पोर्टेंट टर्म जो है उसको हम एलिमिनेट करते हैं। तो 2n plus 3, चूंकि 3 का यहाँ पे ज्यादा कंट्रीब्यूशन नहीं है, तो बिग O इसको खत्म ही करना चाहिए, एंड दैट इज व्हाट वी आर ट्राइंग टू एस्टैब्लिश। सो ऑलवेज लेस देन और इक्वल टू के राइट हैंड साइड में there should be less number of terms than LHS. This is the point which we have to see when we have to fulfill this condition. So we can multiply this n with anyone as long as two conditions are met. One is that the right hand side should follow this condition always, and the right hand side should be less in number of the terms than the LHS. So does this mean that if we move forward and we write so 2n plus 3, the same function, that is f of n, I'm writing it here again, 2n plus 3 less than or equal to, n तो है ही gn के बराबर, because linear को linear ही लेना है, अगर हम लीनियर को क्वाड्रेटिक लेंगे तो वो तो बहुत ज्यादा ग्रो करता है इससे। अब मुझे देखना है कि इफ आई मल्टीप्लाई दिस n बाई 7, that is at this very time if I take c is equal to 7 not equal to 10 as in the previous example, क्या मेरी कंडीशन यहाँ पे भी होल्ड करती है? I have to see this. Okay, so when I put the values of different n starting from n is equal to 1, I see that this will become 2 plus 3, that is 5. This will become 7. So 7 is greater than 5. So this condition will be also true. So I can say that 2n plus 3 here in this example, the previous one, I can say that 2n plus 3 is less than or equal to 10n. Since 2n plus 3 is my f of n, 10 is my c, and n is my g of n, I can see that this condition is satisfying. So I can say that fn is big O of n. Big O of, actually definition क्या है? f of n is big O of g of n. तो g of n यहाँ पे किसके बराबर है? n के बराबर. So I can write f of n is big O of n. But जब मैं 2n plus 3 लेता हूं और इक्वालिटी के राइट हैंड साइड में I just use the n and I multiply this n with some another constant 7. I see that whether at this very time this condition is again holding or not. And I came to conclusion that yes, when n greater than or equal to 1, this condition is satisfied. So this condition, once it gets satisfied, it means my 2n plus 3 is f of n, my c is now c 7, and my g of n is now n. So I can say that this is also f of n is big O of n. Okay, and similarly, if I now there could be different functions which will satisfy this condition. Like in this example, this is also satisfying, this is also satisfying. So which one I had to take big O of n? The point is that. Okay, so which one? If you take the first one, that is correct. If you take the second one, that is also correct. But what is more important? What is more informative? What is more informative is that we take a rule of thumb is that here in this step, you understand, we take 2n plus 3 again on left hand side. Okay, and less than or equal to sign will remain unchanged. On the right hand side, we will take 2n, this 2n, okay, plus we will add 3 to it. That is what is on the left hand side, we will add that on the right hand side and also multiply it with 3. So जो लेफ्ट हैंड साइड में है 2n plus 3 वो राइट हैंड साइड में भी लेंगे 2n plus 3n. 2 और 3 दोनों साइड से लेना है. अब राइट हैंड साइड से n से इसको मल्टीप्लाई करना है और उनको टर्म्स को ऐड करना है. जो भी लेफ्ट हैंड साइड में होगा 2n plus 3n वो राइट साइड में 2n plus 3n लिखना है. सो अगेन अगर मैं और एक स्टेप आगे जाऊं, लेफ्ट हैंड साइड में अनचेंज रहेगा 2n plus 3 लेस देन और इक्वल टू इनको ऐड करके it will become 5n. So this is a rule that which n you have to select, 7n, 10n or 5n. Oh, for that this rule has been given that the number of terms which are in left hand side you just add them and multiply them by n. That is the c which you have to take. So here the c, new c will become 5. So I will now see again whether this satisfies the condition or not. So 2n plus 3 is my f of n, less than or equal to is the condition, c is my 5 now, and n is again the same linear time. So I will see if I put the value equal to n is equal to 1, I see it will become 2 plus 3 means 5, less than or equal to 5 into 1 which is 5. So the condition is satisfied because it is not only less than, it is equal to also. So when I put n is equal to 2, it will become 2 into 2 means 4 plus 3 equal to 7. And on the right hand side, it will become 5 into 2 means 10. So 10 is greater than or equal to 2n plus 3. So this condition will be always true also. So I can say this is also big O of n. Okay. So what I saw here is that we can say f of n is big O of n in all the three expressions. And also, we can say that 2n plus 3, again the same f of n. I'm not changing f of n. It is less than or equal to 2n square plus 3n. As I said, you have to take this 2 on the right hand side, multiply it by n, take and add it with 3, that is this 3, and multiply by n. Here I have taken n square, which is higher term in from linear, it is higher in number. Here if you see, n comes here and n square comes here, which means the rate of growth of n square is more than n. So I am taking a higher function also to see whether this could be also big O of this function, that is 2n plus 3. And when I say 2n plus 3 is less than or equal to, it will get added up. 3 plus 5 will become 5n square. And if you put any value here, greater than 0, greater than or equal to 1, you can say, you will see this condition is also satisfying. So 2n plus 3 will become our f of n, 5 will become our c, and n square will become our g of n. So this function, so we can say f of n is also big O, but of what? N square. This is also true. Even similarly, f of n is big O of 2 power n also. Okay, but we can't write f of n is big. So the point here is, if you look to this chat, the number of functions I have given here, all the functions, since our f of n was linear in time, 2n plus 3, so it was following this function n. All the functions which are on right side of this n, means n log n square, n cube, 2 power n, all those functions could be the big O of this n. You can check each and every of these functions, you will get that this condition gets satisfied in all those functions here. So these all functions whose great growth rate is more than this function, that is the upper bound of this function. Okay, so big O could be any one of those functions which are on the right hand side of this linear function, that's n, that is f of n at this very time. But on the left hand side, whose growth is lesser than the growth of this n, those are known as the lower bounds of this function, Here in this example, we are having the linear function. So if we are having, for example, the log n as its time complexity, so all the terms which are on the right hand side of this log n will become upper bound for this log n, and all the terms which are lesser than this log n, that will become lower bound, but for this function, for log n. So we can say that we can take any of the big O's which are in upper bound of this function. Since it is linear in the present case, so we can take its big O as big O of n square, big O of 2 power n, big O of n power n, anything. But we can't take big O of log n, because this is on the lower side. And what we say, big O always gives the upper bound. Upper bound are the right side functions of this particular. So when we say that so many functions satisfy this condition, all these functions are on the upper bound of this linear function, on the right hand side of this function. So does it mean we have to take all of them? We can take any one of them based upon our choice as the big O? No, the rule is that we have to take least upper bound. Upper bound is this one also, 2n plus 3 less than or equal to 10n. Upper bound is this one also, 2n plus 3 less than or equal to 7n. Upper bound is this one also, 2n plus 3 less than or equal to 5n. Upper bound is this one also, 2n plus 3 less than or equal to big O n square. Upper bound is also fn is equal to big O 2 power n. But we have to see which one out of them is the least. That will be the big O of n of this function. And least is this one. Because exponential won't be least, quadratic won't be least, least will be only linear, and out of that we have to also see whether 7 is least when we multiply it, 10 is least, or 5 is least. The least one we have to take as it is upper least bound. This is very important when we talk about the big O notation. So that is the point which is mentioned here, that while we often use the terminology like 3n plus 3, this is big O of n. Yeah, it is big O of n because it will satisfy that condition given on the previous slide. We almost never say that 3n plus 3 is big O of n square. Even this big O of n square is also true. This is also bigger than that. But the second statement is not informative, it is not corrective, and it is not the right statement. So we take the upper bound, but the least among the upper bound, that becomes the big O of that very function. So similarly, if we go, okay, we will take as an example of this function, suppose this function is 3n square minus 100n plus 6. This is f of n, given it here. This is f of n. And g of n is n square multiplied by 3. So my c is equal to 3. And n square is the rate of growth of this function because this is quadratic in nature. So what I have to see is that I have to see whether this function gets satisfied, on which values this function gets satisfied here. So I will put n is equal to 1 initially and see what will be the value of f of n. So it will be 3 minus 100 plus 6. So it will be 6 plus 3, 9 minus 100, that will be minus 91. Isn't that? So when I put n is equal to 1, 3n square, which is g of n, that will become 3 into 1. It will become 3. So c into g of n means this one. C is 3, g of n is n square 3. Is it greater than or equal to f of n? Huh? This is great. Yes, it is greater than. So I will again check n is equal to 2. When I put n is equal to 2 here, I will get f of n minus 182 and c into g of n will be 12. So again the condition is there. Similarly, I will move forward and I will put n is equal to 100. This will become 3000, okay, and this will become 2006. This will become this much, this will become, always this one is lesser than the, then I can proudly and I can announce that yes, 3n minus n square, 3n square minus 110 plus 6 is big O of n square. Now, omega notation, like I said, that the big O notation gives the upper bound, but which is least in nature. Similarly, the lower bound, which is maximum in nature, the lower maximum bound, that is being given by the omega notation. Some people call it as the best case. It gives the best case of the algorithm. But when we do the deep analysis, these asymptotic notations and this best average, and they don't have to do anything with it. I mean, but for the sake of convenience, you can remember that the big O gives the worst complexity, the omega gives the best, or it means that this algorithm will at least take this much of time, but not lesser than this. So it again means that it will take, if it is very minute amount of time, still it has to take it. It gives the lower bound. And as mentioned in the big O, omega takes this form, f of n is equal to omega of g of n, and is read as f of n is omega of g of n. And the condition here it satisfies is just we exchange the inequality sign. In the big O notation, f of n was less than or equal to c into gn. Here f of n should be greater than or equal to c into gn. The only condition is that remaining conditions are all same. So this means if the running time is this much, okay, So the least amount of running time it will take, that is k into f of n. K is like c into f of n. So the minimum amount of the time this algorithm will take, it should be like this, but not lesser than that. This is the least amount. It can't go beneath that. So again, I won't take any other example. I will take the same f of n is equal to 2n plus 3. Now, I will try to find omega notation of this thing. Now I see on the right hand side 2n plus 3, that is the f of n, that is my f of n. Okay, greater than or equal to, on the right hand side there is n, because this is linear, so g of n will be linear in nature n. Now I have to see which c I will multiply this n with, so that this condition will always get satisfied. This is the point. I had to see that by which term I should multiply g of n, so that my c into g of n will be always greater than, or at least if not greater than, equal to 2n plus 3. And that is where we call f of n is omega of n, because g of n is n, omega is the notation which we use for that. Now see here also, if we like the case we did in big O notation, okay, here we can, since it is linear n, so every function which is on the left hand side of this linear function, that's n, every function which is on the left side, that is the lower bound side of this n. And here in this example, we are having three functions: 1, log n, and under root of n. So any of those functions can be the omega of n. That this is true. But what is important, what is informative, is that we take only the one which is, okay, which is least, maximum least bound. So we take the lower most bound which we are actually need here. And that is why we write it 2n plus 3 greater than or equal to log n. We can also multiply this n with log. That is also correct, because the log n value will be always greater than or equal to 2n plus 3. But we have to take the one which is maximum but least. It should be maximum but least. Like in the big O case, it should be upper, but it should be upper bound but least in nature. Here it should be maximum but lower bound. The opposite terminology. And since 2n plus 3 here in this case is less than or equal to, or we can say 1 into n is greater than or equal to 2n plus 3, so this function is omega n. gn के बदले में n यहाँ पे हम डालते हैं. एंड ओमेगा यहाँ से वही एग्जांपल जो हमने यहाँ पे देख लिया इन दिस केस, इन द केस ऑफ बिग O, द ओनली थिंग इज दैट this statement will now change. Now you see we are having the same function f of n is equal to 3n square minus 100n plus 6, and we say that we have to see whether it is omega of n square. Yes, it will be, because both are quadratic, but the point is that we have to find the value of c and n0. Yes, that is what we are interested in. So when we put n is equal to 1, it will become minus 91 f of n, and this will become 2, because we are taking c equal to 2 here, and 1 into 2, that's 2. So this function, that is g of n is c into g of n is less than or equal to f of n. Okay, but this is not less than. Yes, so this means that we have to apply this condition also. For what value this will be big O, this omega of n, because for this value, if we are taking c is equal to 2, and when we put n is equal to 1, the condition is not satisfied. When we put n is equal to 2, the value of g of n will become, this will be equal to 2, and here it will be n square, means 2 square, 4. 4 into 2 will become 8. And when we put n is equal to 2 in this equation, 3n square minus 110 plus 6, it will become minus 182. So we will again see whether this equation satisfies. C into gn is 8. Is it less than or equal to f of no? Again, we will when we put n is equal to 10, you see we will get 100, it will become minus 694. So their condition is also not satisfied. We will move again to 100. When we put 100, it will become 100 into 100 multiplied by 2. That will become this much. And when we put n is equal to 100 here, it will become 20006. So is the condition satisfied here? C into Gn is less than or equal to f upon yes. And whenever you increase any value from 100 onwards, this condition will be always satisfied. So you can write it that yes, 3n square minus 100n plus 6 is omega of n square when c is equal to 2, n is greater than or equal to 100. Before that, it is not. You can also change the value of c. There is no problem in that. If you can put the c value here equal to, for example, 10, you do this calculation, see whether this value gets satisfied even by just n greater than or equal to n 1. कि 1 से ही ये condition satisfy होती है. That could be also omega notation of this thing. Okay, the thing is, point is that we have to find the value of c and n, and the value should be, both of the values should be greater than or equal to 0. They should not be 0 or negative. Now the third notation is the theta notation. Theta notation is being accepted as the most important notation out of all the three. And normally every algorithm, its time complexity is given in terms of theta. Now sometimes if we are not able to draw the theta notation of any algorithm, then we go to the next two, that is big O or omega. And theta is being accepted as an average case complexity of an algorithm. And like in the big O, it was giving the uppermost bound, here it was giving the lowermost bound, means it in the big O, it can go maximum up to this thing, but not more than that. In the omega, it can go lower up to this thing, but not less than that. Theta gives the exact boundaries कि किसके और किसके बीच में इस फंक्शन का होगा, इस एल्गोरिथम की कॉम्प्लेक्सिटी होगी. इट गिव्स द एग्जैक्ट डोमेन और एग्जैक्ट यूनिवर्स ऑफ एक्सपेंशन ऑफ अ फंक्शन. c1 कांस्टेंट का वैल्यू g1 फंक्शन, c2 कांस्टेंट दूसरा gn, इन दोनों के बीच में ही इस फंक्शन का ग्रोथ होगा, not below that, not upper that. That is why theta is known as the exact time complexity of an algorithm. And again, it's written read as f is the theta of g of n, written as like this. And the condition it should satisfy is that the f of n should be in the middle, and it should be, f of n should be greater than or equal to c1 into gm and less than c2 into gn. Gn should be on both the sides. Function should be only one. It should not be like here we will use n linear, here we use quadratic. Now, if we use quadratic, it should be on both the sides. If we use cubic, it should be on both the sides. If it's linear, the only thing we have to find is c1 and c2, the two constants. So again, we will use the same example, because from same example things will get clear. F of n is 2n plus 3. Now 2n plus 3 is our f of n. We will keep it in the middle as per the formula. So this is 2n plus 3. On the left hand side, we will see is it greater than 1 into n, because that we have found in the omega notation, 1 into n. There it was greater than 1 into n. So here it is greater than 1 into n. 1 is our c1 and n is our g of n. Now on the right hand side, c2 into g of n. Since g of n is again n, which we got from which? omega, big O, this thing, 2 of n plus 3 less than or equal to 5n. This we have already calculated, yes? So we have calculated both the big O as well as the omega, and we will put the values in the theta notation. 2n plus 3 is greater than or equal to 1 into n. Yes, we know. It is also less than or equal to 5 into n for all values of n greater than or equal to 1. You can put any value of the 1, you will always get this condition is satisfied. So from this notation, what we got, g of n is n on both the sides. So the important condition is satisfied. Now C1 is 1 and C2 is 5. So this whole condition which stands for the theta, this is satisfied. So we can proudly say that yes, f of n is theta of n. Okay, this gives the both the upper and lower bound of this function 2 of n plus 3 of this growth. Now again, as we did in the previous cases as a numeric experiment, we will do it for theta also. So like we took 2n square in case of omega and 3n square in case of big O, and the actual function is 3n square minus 110 plus 6. So when we put n is equal to 1, 2n square will become 2, this will become minus 91, this will become 3. Okay, so we have to see, is this condition satisfied? This one? No. क्यों? एक ही जगह पे गड़बड़ है, दैट इज कि ये इससे बड़ा नहीं है ना, इससे छोटा है, एंड वो भी हम चेंज कर सकते हैं इफ यू पुट सम अदर सी हियर, बट आई जस्ट पुट another c here only to make you understand that it is not necessary कि ये 1 से ही सेटिस्फाई करना चाहिए, ये कहीं से भी सेटिस्फाई करे, तीनों कंडीशन को सेटिस्फाई करे, ये ध्यान में रखना है। और यहाँ पे आप तब लिख सकते हो कि ये सेटिस्फाई करता है इस कंडीशन को, बट जब n की वैल्यू ग्रेटर देन इक्वल टू कुछ हो, वो दैट इज करेक्ट वे ऑफ राइटिंग। अगर मैं n से ही स्टार्ट करता है, n ग्रेटर देन इक्वल टू 1, यहाँ पे वो सेटिस्फाई करता, तो ये एक ट्रेडिशनल वे बन जाता, ये हमारे दिमाग में रखते शायद 1 हमेशा ही लेना है, बट दैट्स नॉट द कंडीशन। सो जब इसमें ये सेटिस्फाई नहीं करता है, 2 की वैल्यू में डालता हूँ, दिस इज 8, दिस इज 1 minus 8, so 1 minus 182 is less than or equal to 12. Yes, so this condition satisfy हो जाती है ये वाली, but ये वाली condition satisfy नहीं होती है ना। So I will keep on increasing the value until I reach to a particular point where I put n is equal to 100. At that very time, my omega of n, that is 2n square, that will become 20,000. 3n square minus 100n plus 6 will become 20,006, and C2 into Gn will become equal to become 30,000. So when I use this condition, it means f of n 20006 is greater than or equal to C1 into Gn, which is equal to 2 times 0. Yes. Is it less than C2 into Gn, that is 30,000? Yes. So from here onwards, whatever the value of n you put, you will always see this condition gets satisfied. And C1 you can take equal to 2, C2 you can take equal to 3, but you have to mention the value of n for which the condition is getting satisfied. That is the correct way of representation of this thing. And in all those slides, I will share the previous slides as well as this lecture slides today itself in the group. So all these examples are again the same thing. Like you can say, here I have given some examples, 3n square minus 100n plus 6. Is it big of omega of n cube? No, it's false, because now just by looking at the function, we came to know that this omega is on the right hand side of this function, so it won't be true. 3n square minus 100n plus 6 is less than n cube. So the thing is here, the point is here, this is what I actually want to convey. There will be several functions, like in case of the big O, जहाँ पे बहुत सारी फंक्शन है थी जो कि कंडीशन एफ ऑफ एन लेस देन इक्वल टू सी इंटू जी एन को सेटिस्फाई कर रही थी. Same way, there could be several functions g of n which will satisfy the condition that c into f of n is greater than or equal to g of n. So we can say फिर उसके बाद हमें कौन सी लेनी है फिर जब बहुत सारी फंक्शन हो, which one we have to take. The function is only a lower bound. So for the statement fn is equal to omega of gn to be informative, gn should be as large a function of n as possible. Like in case of big O, there are so many functions which satisfy the condition which is given in big O, but we will take the one which is upper, and inside that upper bound we will take the one which is least in nature. Here the thing is get reverse. We take the one which is large but on the lower side of that function. So if a function is given that is 3n plus 3, its omega notation will be omega of n. Its omega notation is also omega of 1 because 1 is on the left hand side of n, so this is on the lower hand side. So 1 is also true, omega is also true. So we will never take it as this should be omega here, omega of 1. We always take it as omega of n because lower hand side but upper one. And this is which we already discussed yesterday, that what could be the 3 program steps inside some algorithms like the searching as well as the sorting. And search algorithm you have to uh, implement in the lab. uh, yes, and this is an example of the sum algorithm where hang an array with with n elements, and using an iterative approach we calculate the total sum of the numbers inside that array. And using the previous techniques like the tabular method as well as count method, we got its total complexity as 2n plus 3. 2 बार n है, 1 3 बार है, 2n plus 3. This is what we already have done. Now when we do the asymptotic analysis of the same algorithm, asymptotic analysis हमें क्या बोलता है? The least term will be ignored, only the term which grows, whether it is linearly, quadratic or exponential, that will be kept. And here if we write down it in terms of asymptotes, this is 0, this is 0, this is 1 means theta of 1 time, this is n plus 1 means theta of n because 1 will be again eliminated, n this is theta of n, 1 theta of 1, this is 0. So when we add the total number of steps, it will be again theta n plus theta n because 1 and 1 will be also eliminated. So theta n of theta n will be 2 theta n, 2 will be also eliminated. So constant and the lower terms are always eliminated. So we always talk about that the complexity of this algorithm will be theta of n, means its biggest growth will be in terms of the n. Similarly, a function we have also learned about the matrix addition. We came to conclusion that its total complexity is 2mn plus 2m plus 1. Okay. So if we try to analyze it using the asymptotes, it should be that its complexity should be theta of m of n. 2 will be eliminated, 2m will be eliminated, 1. The highest term is mn, yes? And so the mn is 2 will be also eliminated, so it should be like theta of mn. And if the outer loop is denoted by I ranging from 1 to n, it's not m, it's I ranging from 1 to n. Outer inner loop is also denoted by I is equal to 1 to n. So the total complexity in that case will be n into n, which means n square. And that is how the quadratic complexity of a particular algorithm comes into picture. And this is not only the case, if there is one more nested loop, it will become n into n into n. That will become the n cube. So there is one more lecture. This is not so important as far as your syllabus is concerned, but we will cover it on tomorrow. And today, here, you are having the lab today also. So in the lab, I will discuss what experiments you had to implement, because yesterday we had a meeting and we have been given instructions to focus just on the syllabus so that it should be completed, as their exams also should be on time. So we had to also follow only those algorithms which are mentioned there in the syllabus. So we are having two types of searches. One is we call as linear search, and another we call it as binary search. Now, what is the case? We are given an array. This is an array, for example, a of I, and these are different elements inside that array, ranging from 0 to something. It will be n minus 1. और एक item हमें दिया गया है. We are given an item of any value, for example 10, और हमें find करना है कि whether this 10 is present inside this array. Okay. So in linear search हमारा goal क्या रहता है? We compare this item with every element inside this array. पहले इसके साथ हम compare करेंगे. अगर ये item इस location पे 10 है, तो we return that address of the array a of I, जिस पे ये condition ठीक correct होगी. Okay. अगर नहीं तो हम इस I को इंक्रीमेंट करके यहाँ पहुंच जाते हैं, फिर इसको कंपेयर करते हैं. अगर ये इसके बराबर है तो उस एड्रेस को रिटर्न करते हैं. अगर नहीं तो यहाँ पहुंच जाते हैं. ऐसे कर करके we cover each and every memory location of this array or this data structure. So if it is having the n number of memory location, so we cover each and every. In the worst case, its time complexity will be big O of n. Yes, because in the worst case, we have to cover each and every memory location of this. So now, अगर हमें इसका total size जो है n, that is 32. That is 32. So इसका मतलब है कि एक तो हमें we have to reach all the 32 memory locations, and also we have to compare all 32 memory location with our item which we have to search. Double equal to. Yes. Now there is another way of doing it, that is the binary search. Binary search mein, again the array is given which is a of I from 0 to some value, and it should be n minus 1. So the important condition in binary case is that data should be sorted, either in ascending or in descending order. Data should be sorted. So if whenever you have to apply this binary search, make sure that this condition should be initially applicable. अगर sorted data नहीं है, the binary search can't be applied. Okay. Now suppose we assume that the data is sorted. 5 है, 10 है, in ascending order 20 है, 25 है, 26 है, ऐसे करके के total 32 elements है, जैसे इस केस में हमने ले लिया. Now what we have to find is that we have to find item is equal to 20. okay, इसको हमने find करना है. तो इस element का, इस array का जो first element है, that's a of 0, उसको हम मान के चलते हैं this is lower. We assign a variable to it. और जो इसका लास्ट होगा दैट इज ए ऑफ 31 एट दिस वेरी टाइम, उसको हम हाई मान के चलते हैं। और हम एक मीडियन फाइंड करते हैं विच वी कॉल एज मिड पॉइंट। मिड पॉइंट बिकम्स आवर लोअर प्लस हायर divided by 2. So in this case it will become 0 plus 31 divided by 2, only that integer values. So 31 divided by 2, that will become 15. Yes. So 2, 5, 10, 20, 25, 30, ऐसे करके 35, 38, सपोज 0, 1, 2 ऐसे कर करके दिस इज 15 जो हमारा मिड आ गया। सो मिड हमारा 15 आ गया। तो अब हम क्या करेंगे, वी विल कंपेयर इफ ए ऑफ जो मिड है, जो हमारा मिड है दैट इज 15, उस लोकेशन पे जो डेटा है क्या वो हमारा आइटम है, इज दिस द डेटा विच वी आर सर्चिंग, क्या ये 20 के बराबर है, क्योंकि यहाँ पे जो है 30 है तो ये बराबर नहीं है, ठीक है ना। तो हम क्या करेंगे, हम उसके बाद जब ये 30 के, जब ये हम क्या करेंगे, हम इसको बोलेंगे अगर ये इसके बराबर है तो रिटर्न कर दीजिए, रिटर्न कर दीजिए ए ऑफ मिड को, है ना। या ये कर सकते हैं, या जो है हम क्या बोलेंगे, इफ आइटम जो है हमारा जिसको हम फाइंड करने जा रहे हैं, ओके, इफ दैट आइटम इज लेस देन ए ऑफ मिड, ये एल्स में इसकी जाएगा या इफ एल्स में जाएगा। अगर इसके बराबर है तो मिड को ही रिटर्न कर दीजिए, या अगर जो हमारा आइटम है वो इससे छोटा है, क्योंकि हमारा आइटम क्या है 20, वो लेस देन ए ऑफ मिड है, ए ऑफ मिड हो गया 15 पे जो क्या स्टोर है दैट इज 30, ओके। मीन्स ये हमारा आइटम जिसको हम सर्च कर रहे हैं वो इस मिड वैल्यू से कम है। जब इसे कम है तो इसका मतलब है कि दैट विल बी प्रेजेंट ऑन दिस लोकेशन ऑन लेफ्ट हैंड साइड ऑफ दिस एरे बिकॉज दिस इज सॉर्टेड। सो हम क्या करेंगे, हम उसके बाद अगर ये कंडीशन सेटिस्फाई हुई, मैं एल्गोरिथम की बात कर रहा हूं, तो हम जो हाई वैल्यू है जो ऑलरेडी हमारा हाई था दैट वाज दिस लास्ट पॉइंट, अब हम हाई को ये मान के चलेंगे ए ऑफ मिड। अब हमारा लो एंड हाई चेंज हो गया और उस पे हम फिर से ये लॉजिक अप्लाई करेंगे, ये ना। अब जब हमारा ये फिर से फॉर लूप चलेगी, अब उसके बाद अब हमारी जो एरे है, आवर एरे विल बी ओनली दिस मच ऑफ साइज, इट गॉट रिड्यूस्ड टू हाफ ओनली बाय वन स्टेप, ओके। और ये अब हम इसका नया मिड फाइंड करेंगे इसका, क्योंकि अब जो हमारा लो है दैट विल बी 0, हमारा मिड जो है दैट विल बी 15। अब नया मिड हम फाइंड करेंगे, नया मिड अब क्या होगा, फिर से हाई प्लस लो डिवाइडेड बाय 2, दैट विल बी समवेयर इन बिटवीन, ओके। अगर वो मिड, चूंकि ये वैल्यू जो है, अगर फॉर एग्जांपल ये 8 पे स्टोर है 20 जिसको हमने सर्च करना है, अगर हमारा इस केस में मिड बराबर निकला 8 के, तो हम फिर से ये कंडीशन चलाएंगे, इफ ए ऑफ मिड इज आइटम, क्या ए ऑफ मिड पे जो डेटा स्टोर हो वही आइटम है जो हमें सर्च करना है, यस, सो रिटर्न कर दीजिए इसे। This way, we need only few comparisons. We don't need n comparison like we need in the linear search. Yes. So this is what we have to implement in the lab also. And the complexity of binary search is log n to the base 2. Okay. Now, as in the linear case, I take 32 locations as an example total size of the array. So I said its complexity will be in the worst case big of 32 if I had to compare every memory location of this array with the target element. Now if I implement the same array, it is in sorted order and I implement it using the binary search, so at that very time the number of comparisons which I need in the worst case will be log n to the base 2, that is equal to only 5 comparison. And this is how the algorithms can be used, can be designed to decrease the complexity and perform the task which we need. And tomorrow we will give the last lecture of the unit 1 and it will get finished up. After that we will move to the recurrence relation, because at least 2 of your units should be completed before your internal 1. 2 units are in your internal 1 syllabus. So I am leaving it for today. We will meet tomorrow, and in the lab, if you are coming in the lab, okay. If you are not coming, I will give the programs online and share to each and every one of you, and you need to implement at your respective places. And when I then put the assignment you have to submit online. But the programs which we have to do in lab, that will be given to you during the lab time.